All these are examples for a null matrix. The order of null matrix again depends on the number of rows and columns. A rectangular matrix is a matrix where it is not a square matrix. That means the number of rows is not equal to the number of columns. They are completely different. It's a diagonal matrix where principal diagonals are equal. Then we can call it as a scalar matrix. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. In today's session, we are starting with the chapter Matrices and Determinants. So here in this session, I'll be handling the matrices, types of matrices and algebra of matrices. What do you mean by this matrices? Matrices is a plural form of matrix. It is a rectangular arrangement of numbers, elements. They may be real or complex number. So they are arranged in the forms of rows and columns. So therefore, matrices is nothing but it is an arrangement of number. They may be real or complex. So they are expressed in terms of horizontal rows and vertical columns. So here I have taken an example. We always represent a matrix with the English alphabets using capital letters and we write them in a square brackets. So here in the first row, you can see the numbers 1, 3, -2 are arranged in the first row and 4, 5, 6 are arranged in the second row. So this can be taken as a horizontal rows or you can also arrange it in the form of a column. So 1, 4, first column, 3, 5, second column, -2, 6, third column. Like this, we can also arrange any alphabets. For example, let me take matrix B is equal to A, B, C, D, E, F, C, A, B. So like this, we can arrange the alphabets also, which may take different values later. So these are all the variables I can say. We can also repeat the numbers or variables inside the matrices. So here it is only purely the arrangement of numbers in horizontal rows and vertical columns. Next one, we have order of a matrix. Order of a matrix is nothing but the number of rows and columns in terms of matrix. For example, in the previous example, you can say here, matrix A contains 1, 3, -2 in the first row, 4, 5, 6 in the second row. So you have 2 rows here. That 2 rows is usually represented as M and here we have M is equal to 2. And number of columns is here 3 and generally we represent number of columns in terms of N is equal to 3. So how we can say what is the order of this matrix? The order of this matrix is 2 cross 3 or 2 by 3. That means you have 2 rows and 3 columns so that you can also calculate the number of elements inside it. For example, it is 2 3s are 6. You have 6 elements inside the matrix. Similarly, let me take matrix X is equal to 1, 2, -1, 0. So here how many rows you have? You have 2 rows and 2 columns. So therefore you represent it by 2 cross 2 or 2 by 2, which means 2 rows and 2 columns. Let me take one more matrix, matrix P. Here X, Y, Z. So what is the number of rows here? You have 3 rows. So we will write the number of rows first. And here you have 1 column. So you will write this as 3 cross 1. Always order of rows is written first and then the columns. So always in general, we represent any matrix order in the form of M cross N. We read it as M cross N or M by N. Suppose in general, if elements of matrix contain A1 to AN, B1 to BN, C1 to CN, D1 to DN. So you can clearly see you have n number of elements here and you have here 4 rows. So it is 4 rows into n columns because you might have from one column to the last column n. So in general we write it as 4 cross n. So n might also have certain values of natural numbers. So therefore the order of a matrix is always written in the form of m cross n or m by n. So next we come across the types of matrices. So based on the number of rows and number of columns of a matrix, we decide what type of a matrix it is. The first one is the row matrix. As the name itself says, it contains only single row. So for example, matrix A is equal to 1, 2, 3. So this is an example for a row matrix. So let me take one more example. X is equal to 1, 2, 3, etc. n. So you might have number of columns for that, but you will be having only single row. So therefore, here you can represent it as 1 cross 3 and here you can represent it as 1 cross n. So therefore, the order of a row matrix is always 1 cross n. N gives you the number of columns. In the first case, you have 3 columns. You might have 4, 5, 6 and infinite number of columns. But the number of row is always single. That is why the order of a matrix of a row matrix is given by 1 cross n. Next one, you have the column matrix. As the name itself says, it contains only one column. So let me take an example. X is equal to A, B, C. So here you have 3 rows and 1 column. So the matrix which contains only one column is nothing but the column matrix. Here also the order of a column matrix may be represented as n cross 1. Number of rows may be finite or infinite, but the column is always 1. Next one, null matrix or zero matrix. A matrix which contains only 0 as their elements is called as null matrix, and it is always represented by capital O. O represents the null matrix or zero matrix. So it may be 0, 0, 0, 0, or O is equal to 0, 0, 0, 0, 0, 0. Similarly, O is equal to 0, 0, 0, 0, 0, 0. So here all these are examples for a null matrix. The order of null matrix again depends on the number of rows and column. In the first case, it is a null matrix of order 2 cross 2. In the second case, it is a null matrix of order 3 cross 2 because 3 rows and 2 columns. And in the third case, it is a null matrix of 2 cross 3, 2 rows and 3 columns. Next, we come across the square matrix. So what do you mean by square matrix? A matrix in which the number of rows is equal to number of columns. It is nothing but the square matrix. For example, A is equal to 1, 0, 0, minus 1. Or B is equal to 1, 2, 2, 2, minus 1, 2, 0, 1, 2. So clearly in these two examples, number of rows is also 2, number of column is also 2. And here the number of rows is 3 and number of column is 3. So in general, order is always equal to n cross n, or we simply say it as n. Because n represents the same number of rows as well as column. So therefore, the order of a matrix in a square matrix, which can also be written in the form of m cross m or simply m. Next one, Rectangular matrix. A square matrix is a matrix where number of rows will be equal to the number of columns. A rectangular matrix is a matrix where it is not a square matrix. That means the number of rows is not equal to the number of columns. They are completely different. For example, we can take a row matrix as also rectangular matrix. Let A is equal to 1, 2, 3. This is also a rectangular matrix, or it may be a column matrix 3 and 2. So here 2 rows and 1 column. So 1 rows, 3 column, 2 rows, 1 column. So they are completely different. I can take one more matrix. 1, 2, 3, 4, 5, 6. So here you have 2 rows, 3 columns, or 1, 5, 3, 2, 5, 0, 0, 2, 7, 0, 1, 3. So here you can see you have 3 rows and 4 columns. So these are all examples for rectangular matrix. They will be having different number of rows and different number of columns. Again, the order of a rectangular matrix depends upon the number of rows as well as the number of columns. Next one, we have a diagonal matrix. A diagonal matrix is a square matrix. So we can say it is a square matrix. So let me take an example of a square matrix here. So let me take a square matrix 1, 2, 3, 3, 2, 1. Next 2, 3, 1. In a square matrix, we have a diagonal elements from left to right. This is called as the principal diagonal elements. Principal diagonal elements. So this is called as the principal diagonal elements of a square matrix. A diagonal matrix is a square matrix except principal diagonals, all elements are 0. For example, matrix A is equal to 1, 0, 0, 0, minus 1, 0, 0, 0, 2. So here you can see principal diagonal means a diagonal elements from left to right. So this is called as the principal because you are taking from left to right. So this is called as principal diagonal elements. So except principal diagonal elements, if all the elements of a square matrix is a 0, then it is called as diagonal element. Again, the order of diagonal can also be represented as n or simply m. Because it's a square matrix whose order of rows and column will be same, hence the order of diagonal matrix can also be said as n or m. So let me take one more example. B is equal to 4, 0, 0, minus 4. So here also the principal diagonal is not 0. The other elements are 0. Next one is the scalar matrix. Scalar matrix is also a square matrix. It is just like diagonal matrix, but one extra condition is that the principal diagonal elements are equal. So I can write scalar matrix as a square matrix whose principal diagonal elements are equal. And other elements are 0. Or you can write one more definition. A diagonal matrix whose principal diagonal elements are equal. For example, I can take A is equal to 2, 0, 0, 0, 2, 0, 0, 0, 2. So clearly you can see the principal diagonal elements are equal and the rest of the elements are 0. So you can say the definition for a scalar matrix in a two-way, that is, it's a square matrix. Square matrix means again the order will be same because the number of rows and number of columns will be same. Therefore, so we can say a scalar matrix is a square matrix whose principal diagonal elements are equal and the other elements are 0. Or you can say it's a diagonal matrix because we know that in a diagonal matrix, except principal diagonal elements, the rest of the elements are 0. So we can directly say it as a diagonal matrix whose principal diagonal elements are equal. In case of diagonal elements, the principal diagonal elements are not equal. They may be different. But here, the principal diagonal elements are equal. So it's a diagonal matrix where principal diagonals are equal. Then we can call it as a scalar matrix. Again, the order here we can take it as n because again it's a square matrix. I can take one more example, that is B is equal to minus 3, 0, 0, 0, minus 3, 0, 0, 0, 0, minus 3, 0, 0, 0, 0, minus 3. So here also you can clearly see all the principal diagonals are minus 3 and the rest of the elements are 0. So this is an example of a scalar matrix. Next one is unit matrix or identity matrix. Again, unit matrix is a scalar matrix whose principal diagonal elements are 1. So, a scalar matrix whose principal diagonal elements are equal. Elements are equal, or you can say elements are 1. So for example, the unit matrix or an identity matrix is always represented by the capital I and only the principal diagonal elements are equal to 1 and the rest of them are 0. That is why I have mentioned it here it as a scalar matrix, because in a scalar matrix the diagonal elements are equal and the other elements are 0. Here it's a scalar matrix whose diagonal elements are equal to 1 and other elements are 0. So I is equal to 1 0 0 0 1 0 0 0 1. So its identity matrix of order 2 cross 2, its identity matrix of order 3 cross 3. Again, identity matrix is also square matrix. Because it's a scalar matrix is also square matrix, diagonal matrix is also square matrix. So therefore, their order or the number of rows and number of columns will be same. Again, unit matrix is nothing but it's a scalar matrix whose diagonal elements are equal to 1. Next we have equal matrices. Suppose we have two matrices, matrix A and matrix B. If their order is same and if the corresponding elements are same, then we say the two matrices are equal. For example, matrix A is equal to 1, 2, minus 1, 2. Matrix B is equal to 1, 2, minus 1, 2. So here you can see the order of A is also 2 cross 2. The order of B is also 2 cross 2. And the corresponding elements. So first place. So that is in the first place and first column, we can say both are 1. So first row and second column first element 2, 2, minus 1, 2, 1, 2. So therefore we can write A is equal to B here. Take one more example. X is equal to 1, 2, 3, 4, 3, 2. Let Y is equal to 1, 2, 3, 2, 3, 4. So look here, the order of a matrix is here 2 cross 3. Here also the order of a matrix is 2 cross 3. But the corresponding elements, here they are not equal. and here. If the corresponding elements inside the matrix is also same and the order is also same, then only we can say the matrix are equal or equal matrices. So here what I can write, X is not equal to Y. Next one, we have algebra of matrices. So that is, what are the operations on matrices we can have. So the first one is the scalar multiplication. Suppose you have a matrix A. Let me write the elements in the form of A1, A2, A3, A4. So these are the elements of a matrix. If you are multiplying any scalar quantity to matrix A, then you have to multiply each element inside the matrix by the scalar quantity. Let me take, suppose I am multiplying K with respect to A. Then you have to multiply it to each and every element. Ka1, Ka2, Ka3, Ka4. So this is nothing but the scalar multiplication of a matrix. Suppose I have a matrix B is equal to 1, 2, minus 2, 4. So I need now 3B. So if I want 3B, multiply 3 to each and every element of the matrix. So that is, we are going to multiply 3 1s are 3, 3 2s are 6, 3 into minus 2, minus 6, 3 4s are 12. So this is how we are going to multiply any scalar quantity with the given matrix. Next one, we have addition of matrices. So to add any two matrices, the order of the matrix must be same. If they are different, we cannot add any matrices, and for subtraction also the rule is same. So to add or subtract any two matrices or more than two matrices, the order of the matrices must be same. So let me take an example of matrix A. 1, 2, 3, 3, 2, 1. Let me take one more matrix B. Minus 1, 2, minus 3, 3, minus 2, 1. Now clearly you can see this is a matrix of order 2 cross 3 and this is a matrix of order 2 cross 3. As I said previously, to add any two matrices, the order of a matrix must be same. So here they are same. Then only we can add the corresponding element. So you should add only the corresponding element. First to first, second to second, like that. So let me add A plus B now. So A plus B is equal to corresponding element 1 plus minus 1. Next we have 2 plus 2. Next we have 3 plus minus 3. Next we have 3 plus 3. 2 plus minus 2. And last 1 plus 1. So therefore A plus B is equal to, here it is 0, 4, 0, 6, 0, 2. And the order of this matrix will also be the same, 2 cross 3. So therefore, when you are adding or subtracting any two matrices, the order of the matrices must be same. Then only you can add the corresponding elements inside the matrices, and the resultant matrix A plus B or A minus B will have the same order of the two matrices. Let me take an example of matrix X. So it is 1, 2, 3. Matrix Y 2, 3, 0, 2. So here I cannot add or subtract any elements inside the matrices because their orders are different. It's a column matrix of order 3 cross 1 and it's a square matrix of order 2 cross 2. Since their order are different, we cannot define or write X plus Y. We have certain rules which the addition of matrices and scalar multiplication holds. So let's see what are those properties which it can obey. So the addition of matrices and scalar multiple of a matrix satisfy the following property. So if A, B, C are the matrices of same order, I said when you add or subtract, the matrices must be of the same order. So when we have the three matrices here of same order, the first one says commutative law under matrix addition holds. That is, A plus B will be equal to B plus A. So you can see the same thing here. So if you take B plus A here, it is again nothing but minus 1 plus 1, 0, 2 plus 2, 4, minus 3 plus 3 becomes 0, 3 plus 3 becomes 6, minus 2 plus 2, 0, 1 plus 1 becomes 2. So clearly you can see here A plus B will be same as B plus A, and their order is also same. So that is why the commutative law under matrix multiplication holds good. And it also satisfies the associative property between any three matrices of same order. Next, when you have two matrices A plus B and you are multiplying any scalar quantity to it as K into A plus B, that is also equal to Ka plus Kb, which is the scalar multiplication. The last one is when you add any matrix to the null matrix or null matrix to any matrix A, the resultant matrix will be A only. Therefore, we call O or 0 as the identity element under matrix addition, because to satisfy the identity property, there must be one additive element. So therefore, since null matrix contains only the element 0, so when you add any matrix to the null matrix, its value will be always same as the matrix A. Hence, we call O or the null matrix as the identity element under matrix addition. Next, we have one more concept, that is transpose of a matrix. So transpose means changing rows to columns and columns to rows. So let me take one example A, matrix A. I have 1, 2, 2, 1. So write rows into columns, column into rows. So then it becomes again 1, 2, 2, 1. It is always represented by A dash or sometimes A transpose with power T. So therefore, A dash is nothing but a matrix which is a transpose of A. So let me take one more example, X. Have X is equal to 1, 2, minus 3, 3, 2, minus 1. Then what is X dash? So write rows into columns. So it is 1, 2, minus 3, 3, 2, minus 1. So like this. So changing the rows into columns or columns into rows will give you another matrix which is called as the transpose of a matrix. And coming to the order of a transpose matrix, if the order of the matrix is M cross N. Suppose let A is a matrix of order M cross N, then A dash is a matrix of order N cross M. So here it is easy to identify both or 2 cross 2, 2 cross 2. So you will not find the difference here. So let me take the difference here. So here you can see you have 2 rows, 3 columns, whereas here it becomes 3 rows, 2 columns. That's why if a matrix has an order of M cross N, then its transpose will have the interchange of its order, that is N cross M. Next one, symmetric and skew symmetric matrices. Symmetric and skew symmetric matrices are the square matrices. That means their order must be equal, that is the number of rows and number of columns must be equal. So therefore, symmetric and skew symmetric matrices can be only a square matrices. What does this symmetric and skew symmetric matrices mean? So let me take an example of matrix A, that is 3, 1, 1, 5. Find the transpose of this. So that is A dash is equal to 3, 1. Write column into rows or rows into column. 3, 1, 1, 5. So this is same as A only. If the transpose of a matrix is equal to A, then we call it as a symmetric matrix. So this is an example for symmetric matrix. Let me take one more example. Matrix X is equal to 1, 2, 3, 2, 0, 4, 3, 4, 5. So if this is X, let me find out X dash. So let me write rows in columns 1, 2, 3, 2, 0, 4, 3, 4, 5. Clearly you can see here they are same. So therefore X is equal to X dash here. Hence we can say this is a symmetric matrix. Next one, we have skew symmetric matrix. Let me take an example of A. A is equal to 0, 3, minus 3, 0. So let me take the transpose of this matrix. So this is 0, minus 3, 3, 0. So if you take minus outside here, then it is 0, 3, minus 3, 0. So here it is minus A. So when the transpose of a matrix is equal to minus A, then it is called as skew symmetric matrix. So let me take one more example. Matrix X is equal to 0, 2, 3, minus 2, 0, 1, minus 3, minus 1, 0. So let me take the transpose of this matrix, that is X dash. Then it is 0, minus 2, 3, 2, 0, minus 1, 3, 1, 0. So clearly, if you take it as minus outside, then you will get it as 0, 2, 3, minus 2, 0, 1, minus 3, minus 1, 0, which is equal to minus x. So here also x dash is equal to minus x. So therefore, this is an example for skew symmetric matrices. So hence, we can call if the transpose of a matrix is equal to itself, then we call it as symmetric matrices. And if transpose of a matrices is equal to minus A, then it is called skew symmetric matrices. Also remember, in any skew symmetric matrices, the principal diagonal elements will be always 0. For example, I can take A as 0, 3, minus 3, 0. So here the principal diagonal, since both are square matrices, it has principal diagonal elements. So therefore principal diagonal elements of a skew symmetric matrix will be 0. In today's session, we have discussed matrices, types of matrices and few operations on matrices. We'll take the problems in our next session. Until then, keep watching, keep learning, keep exploring. Thank you.